Hello everyone. In this video we're going to look at a technique of integration called integration by partial fractions. So we use this technique often to integrate rational functions. So in order to do this, we're going to look at some integrals, some antiderivatives of some different formats of straightforward rational expressions where the numerator is 1. So starting with, we have 1 over some linear binomial coefficient of 1. So this is basically looking at 1 over x dx, and the antiderivative of this is just ln of the absolute value of x plus some constant. Well, if all I have is a horizontal translation of this, so x minus 6 or x plus 25 or whatever, where the derivative of that function is still, sorry, not a horizontal translation, vertical. If all we have is something whose derivative is simply 1, then that argument is going to be the argument of the absolute value here, and that's what we have. Because x minus 6 has a derivative of 1, we go from there. It's basically not much harder if we have something that's still linear but whose derivative isn't 1. So in other words, my coefficient in front of the x, the leading coefficient, is not 1. We just then need some sort of modifier to adjust so that if we apply the chain rule when deriving this expression, we get the original. So, for example, this could look like 1 over 5x minus 7 dx. Well, this is going to be then simply 1/5 of the natural log of the absolute value of 5x minus 7 plus some constant. So we need a coefficient that's going to essentially cancel out the derivative of that argument. Now, if we have powers, then we're not going to use natural logarithm, we're just going to use power rule. So remembering that if I had, for example, 1 over x squared, and I was anti-deriving that, that would be the same as x to the power of negative 2, which becomes x to the power of negative 1 divided by 1, or for all intents and purposes, times negative 1 plus some constant. So again, if that x is some other expression whose derivative is simply 1, then we don't have to worry about it. If the expression had been, say, 5x plus 3, then we would simply have to also multiply it by 1/5 in order to account for the derivative. And then the last one is specifically quadratics in this format. A quadratic where we have x squared plus 1 is, it anti-derives to the arctan. Now, there are also formulas for what if I have x squared plus 5 or something like that, and that is definitely something you'll explore in university. It's beyond the scope of this course, so we will just deal with ones where we have x squared plus 1 for the time being. All right, so with those in mind, let's look at an expression that doesn't quite fit any of those. So I have the integral of 9x plus 5 over x squared plus x. Now, the first thing I would look for would be a simple u substitution. But if I were to make u equal x squared plus x here, then du is equal to 2x plus 1. And there's no way to just make a simple product of that equal 9x plus 5. So that doesn't work. So this is not going to be helpful. So what I'm going to do instead is I'm going to break this fraction up into simpler fractions. I'm going to express 9x plus 5 over, and I'm going to factor that denominator, x times x plus 1. I'm going to express it as the sum of two fractions whose denominators were x and x plus 1. So two more basic fractions with those individual parts. Because x and x plus 1 share no factors, the lowest common denominator here to put these two fractions together would be x times x plus 1, and that's what I have over on the other side. So each of these would have an unknown numerator. Now, because the degree of the numerator of the fraction I'm trying to break up was 1 less than the degree of the denominator, these are also going to be 1 less. So in other words, if I have a linear denominator here, I'm going to have a linear numerator. And that's simply to make the system of equations that we're about to create work out. We have to figure out what would A be and what would B be. So what I would do then in each case is I would multiply each fraction by the factor that it's missing. So A times x plus 1 and x times x plus 1, and B times x and x plus 1 times x. So essentially what then happens is A times x plus 1 plus bx, those two numerators, have to be equal to 9x plus 5. And more specifically, ax plus bx has to equal 9x, and a has to equal 5. because the linear part and the constant part have to be the same. So if a equals 5 and a plus b equals 9, then that means b has to equal 4. So my original expression is equivalent to 5 over x plus 4 over x plus 1. So that means that the integral I'm trying to find is the integral of 5 over x plus 4 over x plus 1 dx. And each of these can easily be integrated using the rules above. So this is 5 times the natural log of the absolute value of x, recognizing that that 5 is just a coefficient I can factor out, and 4 times the natural log of the absolute value of x plus 1, plus some constant. So breaking up that fraction into simpler fractions with linear denominators makes the integral possible. But what about this situation? We're going to start in the same way. We're going to try and do a u substitution, but if I were to make u equal 2x cubed plus 2x, then du would be 6x squared plus 2, and there's no way that I can make that work out with the numerator that I have, because, du equals this dx, because that numerator has a linear and a quadratic term, whereas this only has a quadratic term, and so it definitely doesn't match. So that's not getting me anywhere. So what I'm going to do instead is I'm going to consider the partial fractions that this would require. So here I have factored denominator, 2x times x squared plus 1. And I need that, I want it to be two fractions, a 2x as a denominator and an x squared plus 1 as a denominator. So something over 2x, and now here's the trick in that second one, because that's quadratic, I need to make this linear. So basically I'm saying if I broke this up into the simplest possible fractions, then the numerators would have to be 1 degree less than the degree of the denominator. So if my denominator is linear, then my numerator is a constant. But if my denominator is quadratic, then my numerator is linear, which means it potentially has two terms. And if I think about that, that makes sense. I have three variables here, and I have three terms in my numerator. I have a quadratic term, a linear term, and a constant term, so I am going to end up with three equations. So getting these to common denominators would be a matter of multiplying that first fraction times x squared plus 1 over x squared plus 1, and the second fraction times 2x, which means that the numerator on of the original, x squared plus 4x minus 3, and I end up with ax squared plus a plus 2bx squared plus 2cx. So now equating quadratic terms, so the quadratic terms are here, so a plus 2b has to equal 1, because that's the quadratic coefficient. Linear terms, well, 2c has to equal 4x. And constant terms, a equals negative 3. Oh, sorry, 2c just equals 4, not 4x. This means that c equals 2, a equals negative 3, and then negative 3 plus 2b would have to equal 1, which means that b is going to equal 2 as well. So once I figured that out, now I know that my fractions are, I have, so the integral of a over 2x, so negative 3 over 2x, and then bx plus c, so 2x plus 2 over x squared plus 1 dx. Now, that second fraction seems to kind of be in the same situation, but what I can do, because x squared plus 1 is a good denominator to have, because I know that's the denominator that leads to an arctangent. So I'm actually going to break that fraction up simply by distributing the division. So I've got the integral of negative 3 over 2x plus 2x over x squared plus 1 plus 2 over x squared plus 1. And now each of these fractions is going to be integrated in a slightly different way. This first one is just going to be a natural log problem. This second one is going to be a substitution problem. And this third one is going to be an arctan. So if I think about this substitution, u equals x squared plus 1, then that means du equals 2x dx, which means that this integral would actually be 1 over u du, or the natural log of the absolute value of u. But u is x squared plus 1. So what I end up with in my first fraction, negative 3 over 2 times the natural log of the absolute value of x, plus the natural log of, now the absolute value of u, the natural log of the absolute value of x squared plus 1, but x squared plus 1 is always positive, so I actually don't need the absolute value signs there. Notice that that 2 is no longer a coefficient because the 2 was required. It was part of my substitution. And then plus 2 times the arctan of x. And then finally, I can add my constant. There are a few more little nuances that come with different types of things we might see in fractions. For example, what happens if the numerator already to start off with has a degree that's higher than the degree of the denominator? And we will look at some more of those in class, but these are the basic principles here.